Okay, today's lesson is 59 Experimental Probability. What's our objective, class? Get ready?
Experimental probability.
Good. Thank you for a good choral response. In this lesson, you will learn how to determine experimental probability using results from an experiment or a survey. We're going to talk about the differences between theoretic and experimental. So, and we're going to be doing some modeling or talk about modeling. So theoretic probability is what the math theory says. If I flipped a coin, there's two possibilities, heads or tails. The theory says heads is 50% of the chances on the coin. So I should get heads 50% of the time, right, Josh?
Right.
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 Okay. So the experiment, though, can show up differently because if I toss the coin one time and I get tails, you say, hey, well, it happens 0% of the time. It never hits heads. But if I toss it a second time, maybe I'll get heads that time. Maybe I won't get heads that time. So sometimes the experimental probability doesn't match up with the theory because you haven't run enough trials. We're going to talk about the number of trials coming right up. Key thing, in your experiment, to calculate your probability, you're going to calculate the number of times your desired event occurs and you're dividing by the total number of trials. That's experimental probability. So let's look at this experiment of flipping the coin. We want to get heads. That's our desired result. So let's say our first trial, we do get heads. So we've had one success out of one trial. Our second trial, we got heads again. I've had two successes out of two trials. So if I stopped right there to say, it's not 50% chance, I have a 100% chance of getting heads. Well, it doesn't match the theory because we haven't done enough trials. Third time, we got tails, so we lost. So we still only have two successes out of three trials. See how 2/3 is about 0.67? That's been rounded. Our heads is our third success out of four trials. 3/4 is equal to 0.75. Our next trial, we lost, so it's still only three successes out of five trials. Heads on the next one, a fourth success out of six trials. Tails, we lost. Still only four successes out of seven trials. Lost again, 4 out of 8 trials. Lost again, 4 out of 9 trials. And then on our 10th one, we finally get a fifth success out of 10 trials, which reduces to 1/2, which we know the percentage is 50%. That matches the mathematical theory because we conducted more than a couple of trials. So here's a sample rise test question. How can you ensure that the experimental probability matches the theoretic probability? Okay, say it again, Lucas.
Do more trials.
Do more trials. And it might ask you, which one would be the best case? 10 trials, 100 trials, or 1,000 trials? You would say 1,000 trials, right? Because the more trials you do, the more likely your experiment will match up to what the theory says. Same thing with rolling a dice. If you've played Yahtzee, you know. Where does this happen in real life? So sports, it happens a lot. It also happens in business and weather and consumerism. So Michael Jordan, he's one of the best basketball players of all time. For 13 years, he played for Chicago Bulls. He shot 50.5% from the field. That means just anywhere 2-pointers and 3-pointers. I don't think it counts foul shots. I'm not sure, though. Better than all 30 NBA teams in 2013-14, and he posted a true shooting percentage of 58%, better than every team except for the Heat in 2013-14. So I would say, looking at this percentage, if he could shoot 50.5%, that would mean if he went right now to shoot a shot, he'd have a 50.5% chance of making that shot. If he shot 100 times, he should make 50.5 of those shots, which you can't really make half a shot. So we could say, well, then out of 200 attempts, he could make 101 of those shots. I could take any number of shots and use that experimental probability to predict what he will shoot the next time he has a turn to shoot. What about Babe Ruth? He's one of the greatest baseball players of all time. It's kind of small, but in 1914, he swung a .300 batting average. What that means is if you move the decimal over 2 places, I never do this when I was a kid because there's always 3 digits, I didn't know why. It's 30.0% of the time he got on base when he was up to bat. Look at in 1915, 57.6%, you move it over twice, he got to base when he was up to bat. So as a coach, you're going to look for your players that have a predictable or a statistically proven experimental probability of the highest number, so you can put them in the strategic place you need to help your team win. So maybe if he's the best batter, you could put him as your 4th batter. That's the cleanup batter, right? If any of you play baseball. If you have someone on first base, second base, third base, because your first player maybe walked, your second player hit a single, pushed the first player over to second, and then you got someone maybe hit a single, and so you've got 3 runners on base. Your 4th batter, if he hits it good, can hit all 3 of those batters into home plate. So maybe Babe Ruth is going to be your 4th batter, your cleanup batter. So we use this in volleyball. When I coached volleyball, here's the net, here's the 10-foot line. If your other team serves that first play of the game, you want to have a good, solid first play. So you want a good passer to touch the ball first. Well, where's statistically the ball most likely to hit on the first serve? It's not going to hit here. It's not going to hit here. Definitely not here. This is a really hard place to serve, and this is a hard place to serve too. The most likely spot the ball is going to land is right there. So who am I going to put here? My best passer. Lucas, Lucas, me. I'm going to put my best passer right there, and probably my next best passer. I usually pull her up to set, but then I'll have my other players here, 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 and here. But I'll put someone who's statistically shown the best record of getting the best pass. It's going to pass it right up to my setter. And then I'm going to put a good hitter here. This person's going to be my best server. So I know that the first time we serve at the other team, they're going to be a guaranteed ace or a guaranteed point over on the other side of the net. All right, so let's look at this case. We've got 21 successful hits in 60 attempts. What's his batting average? I need 3 decimal places. How do we do that? Well, 21 successes out of 60 attempts, we're going to just calculate that right out. 21 divided by 60, and we're going to save time, just type it in. Who's got that? Type in just how it looks. 21 divide 60.
35.
What do you got, AJ? 35%. So he's started here, which equals 35%. Why did I put a 0 there? It just asked. 3 decimal places, because for batting, they always like 3 decimal places. Then we move the decimal over once, twice to change it into a percentage. So this batter has a 35% chance of contacting the ball, hopefully making it to first base. So what if I was shopping? Let's do another application. You ever been to the mall and you're walking down the mall and these like center people are like, here, take a flyer for my business, take a flyer. Here's a coupon for my store, and you're just like, great, now I'm going to have to find a garbage can because I don't want to carry this around. So you wait till they're not looking, and then you find a garbage can and just chuck it. Well, this guy, he's got 50 people took his flyer. 30 people didn't take his flyer. So that means in all, he had 80 people walk past him. Out of 80 attempts, he had 50 successes. Out of 80 attempts, he had 30 not that took the flyer. Yes. What percentage of people took his flyer?
62.5.
Okay, who said it? Make sure you raise your hand so I can call on you. Alex?
62.5.
62.5% took this flyer. What's the percentage here? 3 divided by 8. Who's got that? Let's see. AJ?
37.5%.
37.5% did not take the flyer. So let's apply that. This is my experimental probability. I would assume if I had 1,000 customers, 62.5% of them would take the flyer. 37.5% would not take the flyer. So let's look at this case. They want to know exactly how many flyers I would need if 400 customers were at the store. If 400 customers came up to me, how many would take the flyer? Well, let's figure out 62.5% of 400. Yesterday's lesson we learned how to, before we calculate, we have to change the percentage to what, Colin?
A decimal.
A decimal. How do I do that?
You move it over twice to the left.
Twice to the left. 0.625. And then what does of mean, think, class? What does of mean in math? Get ready?
Multiply.
Multiply or times. Here we go. So
I just said
0.625 times 400. Who's got that calculated? Spencer.
250.
250. So 250 customers or 250 flyers will be accepted out of 400 customers there at the store. Right, Lucas?
It's a lot easier because you already know that 50 out of 80. So if you did 400 divided by 80, then you would get 5, and then you do just 5 times 50.
That's a great way to, you just kind of did a proportion. You said if 50 over 80, then out of 400, what would it be? Lucas saw this relationship. Oh. And then either way would work. Okay, any questions? Got one more thing to illustrate. Coming up in a little bit, we're going to be taking, I got a whole bunch of spinners, I have a bunch of colored chips, and I have dice, I have cards, we're going to put face cards in the game. We're going to be talking about how to model real life scenarios with a small scale experiment, or a small scale, they call it a model. So you can simulate a bigger experiment that's maybe not practical to run. For example, this case they said that a commuter plane arrives on schedule 2/3 of the time on any given weekday. Heather wonders what's the probability is that it will arrive on schedule on a Tuesday, a Wednesday, and a Thursday in the same week. So she could go down to the airport on Tuesday and sit there with her watch and her little sketchbook and tally, okay, that plane's on time, that one's late, that one's on time. And then on Wednesday, that one's on time, that one's on time, that one's late. She can come back on Thursday. It's not that practical, right? Take all day just to drive to the airport. Could I just simulate 2 days of the week, 2/3 on any given weekday, the plane's on time, and then 1/3 of the time it's not on time. So with a 3-part spinner, I could simulate that experiment. So then I could just say, okay, now this is going to be the Tuesday. I'm going to run this experiment and then tally my marks. Then I can say, okay, now we're going to run an experiment for Wednesday and get the results for that. Now I'm going to tally for Thursday. How could I use it? How could I model that same experiment with colored marbles? And I have lots of colors, I have lots of marbles, maybe a bag. What do you think, Lucas?
That's what I was
Okay, give me some specifics though. I'm going to pull them out of a bag, but pull what out of a bag?
So you could grab 2 blue marbles and 1 red marble, put them in a bag, and then you can just have different people reach in and just pick 1 marble.
Okay. And the blue would represent on time, on time. This would be, we'll say no, or late. We'll just say no. And you just like pull them out. So this represents 2 out of 3. How would I do it using numbered dice? I've got a 1, 2, 3, a 4, a 5, and a 6. Someone else will think about it. How would you simulate that, Myron?
Like, 1 and 6 would be not on time, and then all the others would be on time.
Okay, I like your thinking. And then these right here would be on time. So you're saying this would be kind of like an on-time pair. This is an on-time pair, and this is the late or early pair. So I still have the ratio 2 to 3, right? Twice as many as I do my late planes or early planes. That makes sense? Give me a nod if that makes sense. So you just like roll the dice, and then if you land on 2, you say that'd simulate being on time. If I roll a 6, that'd simulate not being on time. As long as this happens twice as much as this. This has to happen twice as much as this. This happens twice as much as this because my ratio is 2 to 3. 2 and 1. So twice as much as this. All right. That is it for today. So you got 2 problems. You take a standard break. I'll tell you what they are after you've stood up.